Thank you very much, Casali and Belati. Or Andrea. It's Brian, that's your first name, I suppose, of Casali. Okay, is everyone, so I think to understand that you communicate from your side by typing, is that correct? I'm just closing the door, by the way. I think to see that there is Andrea, there's me, and then I think I see 6 other names. Are all the 6 of you in one room, or are you all separated at different places? You see 11 people. Wow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 11 people, including Andrea and me. Or are you all looking at your own screen? Is that how it is? 17 people. It's ever increasing. Good. It's a bit slightly difficult that you have to type. So your responses to my questions are a bit slow. So for me, it's easy to talk to you when I've kind of an idea of who I'm talking to and what context you are, whether you're sitting all behind your own computer or that you're sitting in a circle around one big screen, or that there's a different setup. That it's just for the ease of me. It's so could you very briefly say something about that? In English, please, because my Italian is not that very good. Yes, okay, but would it be possible that someone of you or the students can briefly tell me, so I have 2 questions. Are the students all together in one room, or are they separated at different places? And the second question is, yes, but ragazzi rispondete, I'm sorry. I don't understand English. Okay, different places. Yes, very good. Thank you. Yes, good. Thank you, students. This is good. So, and then I guess you're all looking at your own screen. So you're watching me on your screen. Is that correctly understood as well? So you just have the computer in front of you, and that's where you see me? Thank you, Georgia. Okay, and you can also read probably what the others write. So is it correct that you now have the first slide in front of you, which is called climate change, and then the date 19 March is on there, and then you read my name, Reyer Gerlagh, professor of economics. I'm working at the Tilburg Sustainability Center, which is at Tilburg University. Can one person confirm that you see the first slide in front of you? Thank you very much, Julia and Matteo. Okay, so I'll start. Thank you all for joining me. For me, this is the first time that I'm teaching, I'm giving a lecture in this way, so, we'll have to see how it goes. I'm very happy that I can teach you. I understood that you are about 16 years old. Is that also correct? Is that about the age that you're in, so that I have an idea what kind of level I should have in mind? Can anyone write down his or her name, age? Yes, good, thank you. Okay, so what I'd like to tell you about today is a lot of things of climate change. And so I've divided my presentation in three parts: in the history, in the future, and in the present. So first, I'd like to explain to you how the process went, discovering of global warming. What are the basics? What is the mechanism? We all know the word, the greenhouse effect, global warming, but most of us think that this is a complicated physical process. I'll try to show you that it's not that complicated in the end. I'll briefly want to present to you what the major greenhouse gases are, and then I'd like to present to you how we can understand the past, the levels of emissions and the trends that we've seen in the past. And then what that would mean for the future. So what should we expect for the future? What climate change? How much warmer do we think it will become? And then at the end of this lecture, I like to briefly discuss what does this all mean for the actions that we as society would like to take on today. And as I'm an economist, I will mainly focus on what does that mean in terms of cost and benefits of different actions. Naomi, I see all kinds of nice letters. If any one of you has a question that you don't understand something that I try to explain, then please type in the screen the word question or just a capital Q, and then your question, and then I try to watch my screen sometimes to see whether there's an issue coming up, and I'll try to answer it. Yes, you're welcome to, in a kind of interrupt, even though you cannot interrupt by voice, but by writing. So, on the history of climate change. So there are two institutions that are important in this context, which are the IPCC and the UNFCCC. And you should have in mind the following picture. Around the 1980s, the scientists discovered the effect of global warming. That is, they discovered that that global warming might be a potential threat to the future of our Earth. So it took some time to get the message from the researchers and to the politicians, and in 1988, it was not that much thereafter, the United Nations and the World Meteorological Organization, they established the IPCC. And the IPCC is the Intergovernmental Panel on Climate Change. I'll use a pointer, and I suppose that you see. So this is the IPCC, the Intergovernmental Panel. And what you have to understand is that the IPCC is a group of scientists, it's a group of researchers. So these are not policymakers, but these are researchers who try to assess, to kind of summarize the knowledge, the full field of research, in a way that it is useful to policymakers. That is the main purpose of the IPCC, established in 1988. Then, a few years later, the United Nations set also up the political organization, which is the United Nations Framework Convention on Climate Change. So, this is an organization by the United Nations, and it was established after the meeting in 1992 in Rio de Janeiro. This may, for many of you, be in a certain way before your time, but to the people like me who are a bit older, this was a famous gathering. It was called the Earth Summit, where all countries, all members, heads of governments, really, so the presidents of all countries, they came all together to that one place, Rio de Janeiro, and they spoke about their worries for the sustainability of our Earth. And they agreed that climate change was one of the real big worries. And they agreed that they would come together every year in a so-called Conference of Parties, the COP. So the COP is a meeting by the United Nations where all the countries who are member of the UNFCCC. Well, thank you for Brian for that comment. It might be Rio. I haven't seen the video, so I'm not sure. But yes, indeed. So almost all countries are member of the UNFCCC, and they agree to come together and to talk about climate change and what we should do about it. And one of the most famous COP meetings was the third COP meeting in 1997 in Kyoto, in Japan, where the Kyoto Protocol was established. And in the Kyoto Protocol, the rich countries at that time, 1997, agreed that they would reduce emissions and initially, and then the developing countries would agree to reduce emissions at a later stage. And they agreed to set targets for 2012, which is about now. And so the European Union, for example, is a member of the Kyoto Protocol, and the European Union is indeed has reduced its emissions relative to 1990, which was the time, the comparison time then. Now, I'd like to explain to you the basics of the greenhouse effect. I suppose many of you have seen a greenhouse. Here you see a picture of a greenhouse. A greenhouse is it's a glazed house. And the idea is, and you typically use it, say, in spring or in late in autumn, but mostly early in spring, because a greenhouse allows you to have a slightly higher temperature inside the greenhouse than outside, even if you don't have a heating in the greenhouse. So how does the greenhouse work? Solar light comes from the sun, and it can flow, that's visible light, and it can flow easily through the glass. So that's what you notice. If you're in your house and you have a glass, you see that the light can come through. So that's not that shouldn't come as a surprise to you. Now, the visible light goes through the glass, and then it hits the ground, the soil, or the plant. At that very moment, the energy, which is in the photons of the light, the energy is converted into heat. So the soil or the plant slightly heats up. And then from physics, it follows that when a body becomes warmer, it will itself radiate emissions. But the emissions that are radiated by the soil and the plants are of a different frequency. They are of a lower frequency, which is known as infrared. So they emit heat, infrared, and now the funny thing is that infrared actually does not pass through glass. So what happens? The energy can enter the greenhouse as visible light, but the very moment that the plants and the soil have converted the visible light into infrared, it cannot leave the greenhouse anymore. So the heat is trapped. And that's a very simple reason why a greenhouse is warmer inside than outside. So that's the working of greenhouses that you can see around you. It's the same working as that you see in the fields. Often you see plastic type of almost greenhouses. It has the same idea. Now the Earth works as a greenhouse. The atmosphere, that will be the next picture, works as a greenhouse. And what we call global warming is the fact that the Earth, the greenhouse effect of the Earth, works harder than what it usually does. So global warming is not greenhouse effect as such, but it is an accelerated greenhouse effect. So this is a picture of the Earth and the atmosphere. So we have the sun, and the sun emits visible light, and the visible light goes through the atmosphere without too much difficulties. then it hits the earth, it hits the soil, it hits the plants, it hits the water. 30% of the visible light actually is not does not reach the earth. That's reflected back into space before it arrives at the earth's surface. 50% of the solar visible light is used to evaporate water. So water becomes vapor, cold steam, you should think of. And then the remaining 20% is used to heat the surface. So the surface becomes warm, and as such starts to emit infrared radiation. And now the greenhouse effect comes into effect because the infrared radiation actually does not succeed very well to pass through the atmosphere going back into space. So instead of flowing back into space, the infrared radiation actually heats the atmosphere. And that is why it's so nicely warm. Now, the interesting thing is that there are various so-called positive feedbacks. So you noticed already that that half of the solar light is used to heat to evaporate water, and water itself is an important greenhouse gas. So the warmer it gets, the more water there will be in the atmosphere, and the more infrared radiation is trapped, and the warmer it will become. So this is what we call a positive feedback effect. So what are the main greenhouse gases? Well, the main greenhouse gas is water vapor. So, and clouds, which are a special, which actually is not water vapor, but which is water that is just condensed in the air, is also very important. But clouds have a very different effect by day versus by night. By day, clouds reflect solar light back into space, and in that way they actually cool down the earth. By night, clouds trap the infrared radiation from below, so it's trapped through the cloud. So by night, clouds make the earth warmer. So that's the reason, the very simple explanation, and you all must have noticed that if you have a sunny day, typically you have a warm day and a cold night. If you have a cloudy day, then typically you have a cool day and a relatively warm night. That's because the clouds have that different effect by day and by night. And then the second important greenhouse gas is CO2 or carbon dioxide. It is one carbon atom and two oxygen atoms. The main source of CO2 in the atmosphere, the main sources in the atmosphere is simply from the plant, the biological system, where we emit CO2 when we eat some food, or the same happens to animals. We eat food and we convert the carbon in the food into CO2. And then the trees do it the other way around. They convert the CO2 from the air into carbon, which we call wood. So that's a natural cycle. And we humans, we have added to that the emission of fossil fuels, so that's coal, oil and gas. And by doing that, we have added the amount of CO2, we've increased the amount of CO2 in the atmosphere. And then the third very important greenhouse gas is methane. And methane basically are farts from cattle. So whereas carbon dioxide is directly related to our energy supply, the more we fly by plane, the more we drive a car, the more we heat our house, the more CO2 we emit. For CH4, for methane, it's related to the amount of meat we eat. The more meat we eat, basically the more milk we drink, the more cheese we eat, the more cattle we need, and the more they fart and the more methane they emit. Methane is much more powerful as a greenhouse gas, so every molecule of methane captures much more infrared radiation than any carbon dioxide molecule. But on the other hand, methane stays in the atmosphere very shortly. So methane, what we say, it depreciates quickly, whereas CO2 can stay in the atmosphere for more than hundreds of years. Could any one of you, because I typically see students and I see them nodding or I see them looking with amazement, and then I know that they find it difficult to follow me. Could any one of you write down whether you basically the speed, etc., is going okay, or that I'm going too fast, or that you notice already for a long time? Could any one of you just give a brief feedback? Okay, thank you very much, Brian. So now that you know the basics, okay, that's great. Thank you all, Nadia and Matteo. Now that you know the basics of the greenhouse effect, I think actually you can now understand already quite a lot about the Earth history. So let us go look back into the history for 400,000 years. So this is a long, long, long time. Now most people think that the Earth makes a nice circle around the sun and then it turns around its own axis. And that this is a very stable situation, that every year is the same. But actually, this system is not as stable as most of us think. So there are, for example, there are two changes that have very big consequences. One is, and then you see that on the left picture, left upper, is that actually the movement of the Earth around the sun, it's not a nice circle. It's almost a circle. Well, it's more like an ellipse. And the interesting thing is that sometimes it's more an ellipse than another times. And actually, so sometimes it's almost a circle, like what I'm drawing now with the pointer. And sometimes it's like an ellipse, like what you see. And when the Earth turns around the sun like an ellipse rather than like a circle, it means that at some points in time in the ellipse, the Earth is really much closer to the sun. And when the Earth is much closer to the sun, it's really warmer. So with an ellipse, you'll have, say, for example, you have warm summers and cold winters. But in the warm summers, a lot of ice can melt. So you can imagine that if you have an ellipse shape of the Earth orbit, then more ice will be melted in the summer, and as a result, there will be a slightly slower amount of ice on the Earth, and as a result, there will be less solar radiation radiated back, mirrored back by the ice. So ice works as a kind of a cooling device, because ice reflects back all the solar light that comes in. Now, if we have a less amount of ice, so there's more amount of solar radiation that's converted into heat. So the Earth will become warmer. There's also another mechanism, which is that the axis of the rotation is sometimes more tilted than other times. Well, there are many of these phenomena going on. And if you calculate these through, you can actually, you see that many of these mechanisms, they can explain why in some instances here the temperature is much higher on the Earth than in other instances. So that is because of the strong feedback mechanisms of climate change. Yeah. So we are currently at a warm temperature. If we go back about 20,000 years in time, then the Earth was in a so-called ice age, and it was about 10 degrees colder than it's now, 8 degrees colder than now. If you then go back another 100,000 years, you were at the same point in the cycle, and it was another ice age. So here you see ice ages, and then you see a warm period. You see a small ice age, and then you see a moderately warm period. Small ice age, moderately warm period. A real deep ice age, and then suddenly you see a real warm period over here. Thank you very much, Brian, for the question. So I did not explain very well what was on the axis. So my apologies to that. So I'll tell you what's on the axis. So here are years. And this point here is 400,000 years back in time. And this point here is now. And this point here is 100,000 years back in time. and this is 50,000 years back in time. And this curve tells you how warm the Earth was at that point in time. So this curve tells you that it's now warm, but 20,000 years ago it was colder. 50,000 years ago it was colder. No, you're completely right, Brian. Thank you. So this is very useful also to the other students. If really I forget to tell you something, you should ask me. Now, you may forget about this graph for a moment, but so the upper graph is the temperature. Now, also what you cannot see is this is the 0 over here, so that is the current temperature, and we have a 2 over here, which means that this line is the line where it is 2 degrees warmer Celsius than now, and we have a -8 over here, which means that this line are all the points where the temperature is about 8 degrees colder than now. So what you see here is a cycle. I have to click away something. You see a cycle where about every 100,000 years the cycle is repeated. And within such a cycle of 100,000 years, you have a warm temperature and then a warm point, and then it slowly cools down. And then it gets warm again, and it will slowly cool down in the future. And then it will get warm again in 100,000 years' time. So that's what this picture tells you. Okay? So this is already quite interesting. So we think of our Earth as a stable system, but we know from the data, these data come from so-called ice cores from Greenland. We know that in the past the temperatures have been much higher or much lower. So for example, 30,000 years ago, when it was much colder than now, 8 degrees colder, at that time much of the sea was actually converted into ice. The North Pole was vastly larger than it's now. And because all that water was captured as ice, and also as ice on the land, the water that water that was ice was not in the ocean. And as a result, the level of the sea actually at the time was much lower than now. So at the Ice Age, you could walk, for example, from the Netherlands to England because the channel, the sea between the Netherlands and England, it was dry. Because all the water that now is there, at that point in time, was somewhere on the land as ice. Yeah, so that is a kind of a story that this picture tells you. Now, so you see huge variation in the cycles, and I find myself this already quite exciting. Now, also notice, if you look at this, that simply by looking at the regularity of this pattern, actually what the scientists expect is that we will enter another ice age in about 10,000 years. So, if you would live long enough by whatever technology, there's no reason to assume that the Earth will be as nice and warm as it is now. No, the most reasonable expectation is that in about 10,000 years' time it will be quite cold on the Earth. Yeah. Now, here we look into more detail. We focus into the last 5,000 years. So you see here, this is the year 0, the year of Christ, before Christ, after Christ. So the year 2000 is about now. This is about the year 3000. This is the time when the Minoan, the so-called late Bronze Age, when the Minoan kingdom was the main kingdom in the Mediterranean area. This is the so-called Roman warm period. So that is when the Roman were the main power, and this is the medieval warm period. So in the Middle Ages, around the year 1000, also temperatures were relatively high. Now what you see is you see here the temperature slowly going down, and you see that there again is a cycle of, in this case, about 1,000 years time, slightly more than 1,000 years time. So what we expect, if we will look here, we expect that by the year 2150, the temperatures will again be slightly higher than they are now. So, and this has nothing to do with anthropogenic emissions of CO2. This is only because of natural variation in the tilt of the axis of the Earth and then all other kinds of simple mechanics of the Earth. So, one thing to learn from this is that we have a huge, quite a substantial variation. If you look at the temperature here, it runs from 32 to 29, so this is 3 degrees Celsius. So the current temperature is about 2.5 degrees colder than the temperature 3,000 years ago. Yeah? During the Roman time, the temperature was warmer than it's now. During the Middle Ages, the temperature was warmer than it's now. This, by the way, is specific for a specific site. It does not apply in every place on the Earth equally. But anyway, the point is that what you can learn from this is that if temperatures would go up by, say, 2 degrees Celsius, we would be back at the same situation as in the Minoan Kingdom. And actually, you may quite like that. Though the 2 degrees Celsius would actually be in Greenland, so it would be much less than 2 degrees in the Mediterranean area. But so, the point, what's the GISP2 temperature? So, this is a very good question, thank you, Brindisi. GISP2, so in the natural sciences, there are different, collecting data as such is very important. So GISP2, it refers to a team who have collected data, and I think it's Greenland. I think the G is for Greenland, but I don't know the details. They've collected data that allowed them to calculate what the temperature was. So, and this is known, then that series of data is known as the GISP2. And the reason is that then if in natural research you use that data to prove a certain argument and you mention the data, then everyone knows exactly what is the data source, the ultimate data source that you refer to. So it's GISP refers to one collection of data at one point, and I think it's Greenland. So you can see here that if you would add 2 degrees Celsius, that might not be so bad. If you would add 5 degrees Celsius, you would end up somewhere over here. Or if you go back to the chart, adding 2 degrees Celsius would bring us somewhere over here, which is not that bad, but adding 5 degrees would bring us somewhere here. And then we would be way above what we have seen in a very long time of history. Yeah? So the point is, it matters how much the temperature will rise. Now we're still not there. If you look at the last 150 years, so these are the temperature data from another series, you see, interestingly, you see again kind of the same thing. The temperature is not stable at all. This is the global mean temperature. So this is the temperature of a whole series of places of the Earth and then all averaged. And again, you see that there are lots of cycles going on. So one cycle is the one that goes up and down very, very frequently. So that's the solar cycle. So every 11 years, we have a higher or lower intensity in sunspots. And it has a very clear, very measured effect on the temperature. But you also see this cycle, which has a cycle. So here it goes down, up, so it goes down again. So this point is about comparable to that point. So that's a cycle of about 50 years. Yes? So it goes down, it goes up. So you would expect that that second cycle brings us down a bit by now. Sorry, I didn't have the pointer. So here in 1880, it goes down, then it goes up, and then it goes down. So you compare this point where it starts to go down is this point, and it's 50 years. And then you expect that actually here, now, the temperature would go down again a bit. So the last about 10 years, the temperature rise has not been very high, and that is completely in line with what you would expect if you look at this graph very carefully. So, but in addition to all the cycles, you see the stable upward trend. Now, so having seen the previous two charts, I hope you understand that it is a very good question to ask. Which part of this upward trend, so we see the trend going up, which part of this trend is because of humans, and which part of this trend is just part of all the cycles that we've seen here and that we've seen here? Yeah, so this is very volatile. So some people say that, well, this is just part of the natural variation. The majority of the natural scientists think that actually the largest part of this overall increase is because of the human-induced CO2, extra amount of CO2 in the atmosphere. Yes. So indeed, Brian, the majority think that actually the red part, you could say, is kind of induced by human CO2 emissions. But my point here, what I want to teach you, is that it is not crazy that researchers ask whether you can actually make this point. Yeah, so indeed, the majority think that this is caused by humans, but there are skeptics who say, no, this is just part of the natural variation. And hopefully you understand, given the previous two graphs, you understand that it's indeed very hard actually to prove that this increase is caused by humans, because it's very hard to disentangle all the different types of variations. So now let's look at one of the causes of, so here we see the increase in the temperature. Now, the main reason that we think, that most researchers think that the temperatures increased by so much, so they increased by about 0.8 degrees over the last 100 years, is the emissions of CO2, so the amount of CO2 in the atmosphere. Here we see the emissions of CO2 from fossil fuel combustion. So this is basically energy, coal, oil, and gas. And what we see is that you see the Industrial Revolution taking off in England. That's what happened here in 1980. So this is the Industrial Revolution. And then you see that Europe joins, and the US, we join England, and you see that our emissions go up very rapidly. Here you see that the Second World War breaks out. But after the Second World War, we continue to grow and we continue to grow, and we have a very rapid growth. This actually is Europe, what you see here, after 1950. This is Italy becoming industrialized, etc., and the Netherlands and Norway and all these countries in Europe. That's what you see here. But then you see that after about 96, this is by the way the oil crisis, and then you see that at the same point, the Eastern European countries, so this is Russia, the yellow part, they grow together with the OECD countries. But you see that after 1950, suddenly the emissions in Russia, actually they start to drop. This is the decline of Russia. This is the fall of here you see, for example, the fall of the wall in Germany. You also see that the emissions in Europe and the US, they kind of, well, they do not exactly stabilize, but they grow less rapidly than before. But you see especially that Asia takes off here. So what's happening here is Japan. So first Japan takes off, then Korea takes off, and then all the Asian countries take off. And here China, actually. China at the end, currently China emits more CO2 from fossil fuels than the US. So the China per capita CO2 emissions is in about the same order of magnitude as the CO2 emissions in Italy. So that's what you see here, and we'll talk later what we should expect in the future. You see that, by the way, green, that is then Latin America, and sand color is Africa, you see that these two are also, well, they contribute substantially, but in relative terms, it really, what matters most is what happens in Asia and what happens in the OECD. So we want to understand this graph. We want to understand what this graph will mean for the future. So we use a very simple mechanism. We think, why would emissions go up or go down? First of all, if every person emits the same amount, by the way, I'm going to give myself a drink because I'm talking for a long time now. If every person emits the same amount, then obviously the more people there are, the higher the total amount of emissions. On the other hand, if the number of people is constant, we could say that and every amount of goods that we consume, every car, for example, or every kilometer we drive, has a certain amount of petrol that we need, a certain amount of emissions, then it's simply the more we produce, the more we consume, and the more we emit. So that might be the second reason why emissions go up or down. The third reason for emissions going up or down is that maybe you drive a certain amount of kilometers in your car, but if you're driving a more fuel efficient car, then actually the emissions of the car can go down. That's the third reason we want to look into. And then the fourth one is, well, you may use a certain amount of fuels, but it can be different whether the fuels actually are biofuels or that they are fossil fuels. You can use a certain amount of fuels in your electricity plant, but coal has a higher amount of CO2 per energy relative to gas, for example. So if you use coal for your power plant, you emit more CO2 than if you use gas for your power plant. And we write that down, that insight, we write it down nicely as an identity. So the identity says that the total amount of CO2 emissions from fossil fuels is equal to the number of people that there are, times the income of the average person, so the amount of euros per person that we earn, times the amount of energy we need to produce 1 euro of output, times the amount of carbon we need to produce 1 unit of energy, 1 joule. So you can nicely see, if you multiply all these terms on the right hand side, then the joule here can be cancelled against the joule there. And the euro here can be cancelled against the euro there. And the capita here can be cancelled against the capita there. And what we are left with then is only the amount of CO2. And that is indeed the amount of CO2 emissions. So I'd like to make clear, does everyone indeed understand this, one of you, this identity? Because this identity is a very important insight from the literature. Can one of you write down whether this identity is clear to you? I'm waiting for input by one of you. Are you still there? Okay, thank you very much, Matteo and Julia. Tea time, okay. Tea time, what does that mean? That we'll have a break of 5 minutes, 10 minutes or so? Yeah? Okay, I'll be back in 5 minutes. Is that good, Andrea? Okay, I'll be back in 5 minutes. See you in 5 minutes. I'm back to my virtual lecture, Mr. Lezione.
Back to your
Virtual lecture.
virtual lecture.
All the students can see you, you know. This is my esteemed colleague.
Oh,
Go down and I only see your belly.
yeah, they're always impressive, of course, but
This is my
so
esteemed colleague.
who are your
Lezione.
students?
They are there, but their connection is too slow to have their also videos working. So
Okay.
you see, they're all saying hi to you.
Oh, wonderful, wonderful. Hi to you all. Is he a good teacher, my colleague?
Oh, come on. You know how to answer now. Thank you very much. Yes, good.
Oh,
Okay, you may
wonderful.
come.
Wonderful. Hey, I'm not gonna disturb you.
Okay, well, you can tell me when you're ready to for me to continue. Okay. Well, there are at least 3 or 4 already. I'll just continue then. Good. Thank you all. So, what we'll do, we'll look at this identity, and then we'll, simply by looking at charts, we'll ask ourselves whether we understand that emissions go up mainly because of more people, or because we produce more goods, or because we need more energy, or because we emit more CO2 per energy. So that's the next chart. So this chart, we see on the horizontal axis, we see the number of people, and it might be a bit difficult, tricky for you, because this is what we call a logarithmic scale. So here we more than double the population from 0.2 billion to half a billion, and then we double it to 1 billion, then we double it to 2 billion, and we double it to 4 billion. Now what you see here is that, for example, Asia, the population in Asia has grown from 1970, which is this point here, to 2010. Population grew from 2 billion people to 4 billion people. So this is really amazing. You know, the number of people grew by factor 2 in 40 years. This is huge. And what do we see? Yes, we see nice and clearly that the more people there are, the higher the emissions, because that's on the vertical axis. The vertical axis is the emissions in gigatons, and a giga, that is a million, 1,000 million. So a giga is, well, it depends on the language, whether you call it a billion or a milliard. Anyway, 1,000 billion. So you see clearly the pattern is more people is more emissions. You also see that actually in the OECD, in the rich countries, the number of people did not increase very much. And you see that, for example, in Africa here, the number of people increased a lot as well, like in Asia. You also see that the slope in Asia is steeper, and a steep slope means that actually the emissions increased more than proportional to the population size. So the emissions per person grew in Asia very rapidly over time. But still, per person, Asia has, and we can read that here, I'm not sure whether you can read it, but I can read it. Asia has currently 5 tons CO2 per person per year, whereas the OECD is currently at about 15, between 10 and 20, 15. So we emit per person about 3 times as much as the average person in Asia. But then within these regions there are huge differences again, because within the OECD we have the United States and we have Europe, and in the United States people emit twice as much as in Europe. And in Asia, the people in China emit twice as much as the people in, say, Vietnam. So as a result, the people in the OECD who emit the least amount, like people in Italy relative terms, emit about the same per person as the people in Asia who emit the most. But the point here is, the take-home message here is more people means indeed more emissions. That's very clear. So this is a bit more difficult. Here we have the income per capita, so how rich we are on the horizontal axis and how much we emit per person on the vertical axis. And we see here that for Asia, the red line, we see that income has gone up and at the same time that emissions per capita has gone up as well. So there is a clear relation. The richer you are for China, the more you emit. But we also see the blue line that for the OECD, the rich countries actually, we have grown much richer in the past 40 years, but our emissions per capita have not gone up. So what we can learn from this graph is that when you are at a low level of income and your incomes increase, then your emissions increase alongside. But if you then grow ever richer, your emissions will tend to stabilize. So the sad truth is that when you're poor, getting richer means you pollute more. When you're already rich, getting richer does not add that much to your pollution, you could say. It's not as simple as that. Here you see a specific the amount of income versus the amount of energy you use. And you see that indeed, again, Asia, but also Latin America, the green line, Africa, the sand line, they have increased their income levels substantially, and the energy levels, the vertical axis is energy, the energy levels increased alongside. And you see that slightly for the OECD there also has been an increase in the energy use. Not so much as for the other countries. So there is an increase between income and energy use, but the elasticity, that's how we call it, is larger, the relation is stronger when you're poor. And here we see the amount of energy we use on the horizontal axis, and on the vertical axis we see the emissions. And here we see very clearly that the more energy you use, the more you emit. And the reason is fairly simply this. The main energy source that we use on the earth is fossil fuels, is coal, oil and gas. And then it's as simple as this. If you want to use more energy, you would have to burn more coal, oil or gas, and that means you emit more. Here on the right hand side, by the way, you see for coal, oil and gas, you see how much CO2 we emit for every megajoule of energy that we want to get out. You see that coal is the most polluting fossil fuel and gas is the least polluting fuel. And you also see that if you would be able to switch towards clean energy sources, renewable, hydro, it would potentially be possible to have no emissions for our energy use, and then it would be possible to go down along this curve. So, to summarize this last part, what have we learned? More people means more emissions, more income means more production, means more energy, means more emissions, but it grows less than proportional when you're rich. And this tells us that we have basically four options available. The first option is to have, if you want to reduce emissions, to reduce the greenhouse effect. First option is to reduce the number of people. And you can think of the one-child policy in China. The second option is to reduce our income. And that is to say, let's think that less is more. Let's be happy when we're poor. Small is beautiful. The third option is to save energy. That is to try to produce the same by using less energy. And an example of that could be, for example, the Toyota Prius or insulating your house. The final fourth option is to decarbonize energy, which simply means that you want to produce energy without the use of fossil fuels, so that you do not emit CO2. And this allows us to look into the present. But before I do that, I'm not sure how long. I think I have still 4 slides. If Andrea, if you feel that I'm running out of time, you should tell me, then I can almost skip to the last slide more or less. Because the next slides are interesting but also a bit complicated. So they will take some time. Maybe you feel I don't have the time and I should now try to bring it to an end and give the students the possibility to ask questions. But otherwise I'll continue. So what we've seen what the greenhouse effect is, the climate effect is. We have seen what the drivers are, the population growth, energy use, income growth, and carbon use of energy. And now we want to know what does this mean for the future. So, by our use of fossil fuels, we expect to add the amount of CO2 in the atmosphere by 2 teraton of CO2. That's an awful lot. But what it basically means is that we expect that by the year 2050 or so, the amount of CO2 in the atmosphere will be twice as much as the amount that was in the atmosphere 200 years ago. That's what we call doubling the natural amount. And the basic physics tells us that the very first effect of that amount of CO2 will be here that the atmosphere will work as a better greenhouse, and therefore the temperatures will go up by 1 Kelvin or 1 degree Celsius. That's the same. But then the models also tell us that because of that 1 degree Celsius temperature increase, then there will be extra water in the atmosphere, there will be less ice and snow cover, and there will be a lot of series of feedback effects. And because of these feedback effects, the temperatures go up by another 0.7 degrees Celsius. And that extra warmth will lead to, again, extra water in the atmosphere, less snow cover, less ice cover, etc. And then the temperatures go up by another 0.35 degrees Celsius. And then we have the same positive feedback mechanisms again and again and again and again, etc. And if you count together all these feedback effects, then the expectation is that the temperature will rise by about 3 degrees Celsius in the long run that takes about 70 years after we have doubled the CO2 in the atmosphere. So, and this formula in green, the pi at the end. So this is what in the climate science we call the climate sensitivity. So it says that the climate sensitivity, the expected climate sensitivity is about 3 degrees for 2.1 teraton of CO2. Now, if we want to understand what that means for current day policies, we have to understand why we would worry about climate change. There are 2 different types of reasons. One is economic damages. So if the world is warmer, we expect to have more hurricanes, to have sea level rise, and that will mean higher dikes in the Netherlands. We expect that in the countries that are currently warm, the agricultural production will go down. But on the other hand, we also expect that countries that are currently cold, like large parts of Russia, actually agricultural output can go up. But certainly equally important to the economic damages are the intangible damages. So if the earth becomes too warm, it's possible that the Amazon, for example, dries out. It is quite probable that the coral reefs will die out on a very large scale. It is highly probable that the ecosystems that currently live at the top of the mountains, they move up when the temperature goes up because they want to keep it cool, and at some point they have nowhere to go and they will simply vanish. Similarly, the ecosystems that live close to the North Pole, they will move north. The ecosystems close to the South Pole, they will move south, but at some point they can't move further and they will vanish. So, in the economic analysis, what we typically do is we try to make an estimate for how much will the damage be. And a typical estimate is that economists think that the economic damages, so these damages here, that there will be around 3% of our GDP if temperatures increase by 3 degrees Celsius. Now that means that we will lose 3% of GDP And if our GDP is 60 trillion euros, that is then about 1.8 trillion euro per year for an amount of 2 teraton of CO2. So we can readily calculate that the cost of emissions in that case would be 0.8 euro per ton CO2. So that is the cost under these assumptions of a certain amount of CO2 in the atmosphere. So and we used delta for the damages, pi for the climate sensitivity, and the product of the two then is the price of CO2 in the atmosphere. But it's not all. It's now becomes really a bit interesting and complicated. Because if you emit a certain amount of CO2 in the atmosphere, it does not stay all there. Because a large part of what we emit in the atmosphere is taken up by the trees. And another part of the CO2 we emit in the atmosphere is taken up by the deep oceans. So in the end, the blue line is the amount of CO2 that we expect that remains in the atmosphere after we emit it. And you see that after 100 years, about 25% of the CO2 that we have emitted is still in the atmosphere. So 75% has been taken up by trees and the oceans. And you also see that in the very long run, most models expect that about 15% of emissions will remain in the atmosphere, well, in a certain way of speaking, forever. Yeah, so that means more than 1,000 years. Now, also, you should realize that the temperature, I explained it with the positive feedback, temperatures adjust only very slowly. So, the temperature adjustment is the red line, and it moves towards the blue line, and then when the blue line passes it, it moves down. So, if we emit 1 unit of CO2, then the red line tells you actually how much the damages will be because of that 1 unit of emissions. And this is now the big trick. What an economist now can do, the economist can now go back here and say, look, here we know how bad CO2 is in the atmosphere. And here we know how long it takes for 1 unit that we emit to have that effect in the atmosphere. And now we can kind of multiply the two. There's one additional trick that we want to do, and the economist says we actually don't care that much what happens after 100 years. That's called discounting. So we take the whole area under this red line, but we discount the future. So what happens here, we consider after 400 years, we consider less important than what happens here after 200 years. And we think that's less important than what happens after 100 years, and that's less important than what happens, say, right now. Now, and then you go through a bit of mathematics, and you don't need to fully understand that, but the interesting thing is, then this is actually, you get a nice formula here, and what's nice here is that the formula has our expectations on the damages, which is the delta, our expectations on how sensitive the climate ultimately is, the pi. Then it has the current income level, because we think that many damages will be proportional to our income. And then here we have a complicated term. So you may forget about that. The only thing you may want to know is that there is also a discount factor over here. And this formula is nice because it allows you to ask yourself, how certain are we about all these variables, these parameters? So we are not very certain about climate sensitivity. It might be that the Earth becomes 3 degrees warmer, but there are also climate scientists who say that the Earth becomes 8 degrees warmer if we double the CO2. So pi may be 3, but it may also be 8. And similarly, there are some people who say that the damages are 3% if it gets 3 degrees Celsius warmer, but other economists say that actually, it will only be 1% of GDP. So the delta may also be very uncertain. And if we add all these uncertainties together and we throw them into this formula, then we can calculate what the social cost of carbon, so the carbon price, would be, and how likely it is that the carbon price will have that value. And that is what this curve is. So this is really a complicated curve, but if you understand it, it could be very nice. So this curve says that actually the biggest chance is that the carbon price is not very high. It's only about 5 euros per ton CO2. But you have about 50% chance that the carbon price, the cost of CO2, is less than 50 euro per ton CO2, and 50% chance that it's more than 50 euro per ton CO2. And you have even 5% chance, now you have 6% chance that the carbon price is actually more than 100 euro per ton CO2. Now, why is this important? So that's the number over here. If you realize that our current emissions are 40 gigatons of CO2, and so you multiply the price of 100 euro by 40 gigatons, you realize that the damages that we cause to the climate are currently, possibly with a probability of more than 6%, damages are more than 4 billion euros, no, 4 trillion euros a year. So that gives you an understanding of how big the damages are that we currently cause to the Earth by our climate change emissions. So we may want to know if these are the possible costs of emissions. So what would be the cost to reduce emissions? So this is, I think, the final slide, only even though the number doesn't suggest that. So the economist says we want to continue reducing emissions until the cost of reducing emissions is about the same as the cost of letting the emissions go up. So we've seen 4 options to reduce emissions. We can try to reduce the number of people. That's over here. You could say that's what they do in China, but that's very hard. Actually, many people, a lot of people will get mad at you if you tell them that they should have fewer children. And Italy is doing, in that sense, kind of a good job. I think you already have a fertility rate below 2. So the number of people in Italy is already decreasing. But it's not something that you can easily imagine as an instrument for climate policy. So the second option here is to say, well, there's only one solution. If we want to emit less, we have to earn less. Small is beautiful, less is more, etc. But this is very costly because you can reduce emissions only one by one then by reducing income. So the cost of reducing emissions would then be about 1,200 euro per ton CO2. So that is really an awful lot. So I don't think that's very advisable as a mechanism. The third option is if you want to reduce energy use. So, and this option actually is probably the best option for quite substantial reduction levels. We can reduce our energy use by 50% at a moderate cost. The estimates are that the costs are between 0 and 50 euro per ton CO2 if you want to reduce our energy use by a factor 2. So, and this number, the 50 euro per ton CO2, that is in the domain of what we find here on this graph as the possible costs. Yeah? So this whole area, you could say, can be covered by energy savings measures. The final measure that we have is to find decarbonization of energy. So to develop, for example, solar cells and windmills. And typically we think that this is, at the current state of technology, this is more expensive than energy savings. But the advantage is that you can reach much deeper cuts. So energy savings, you can go up to 50%, but by having a different type of energy, actually, we can reduce emissions to 0. So, and this option, decarbonization, that is most useful either if we further improve our technologies, so if solar energy becomes cheaper, for example, or windmills become cheaper, or if we find out actually that the estimates should be in this range of the real price of carbon. So overall, what the research finds is that what we think is the optimal policy is that we should start quite readily now with energy savings as the main way, the main tool to reduce our emissions. And this is we think cost effective in the sense that it doesn't cost that much and it will save probably quite a substantial amount of damages in the future. At the same time, we should develop clean energy because we want to try to bring down the cost of cheap energy below the cost of 50 to 50 euro per ton CO2. If we succeed to do that, then we could in the future reduce emissions much more. Now, if for some reason you think it's not fair to discount future damages, because you have to realize that under this graph, I had the assumption I explained to you that damages that happen in the far future here, this is say the year 2200 at the year 2300, and these damages don't count that much in the calculations that I used to find this curve. Now, if you think that the future should count much more than what the typical economists like to do, that means that you want to have a fair world. Yeah? And if you want to have a fair world, or if you think that actually that we are destroying ecosystems because of climate change, that is morally bad, then that would mean that you would like to do more. So I think this was my presentation. Yep. So you're welcome to ask any questions. Thank you much for your attention, and please go ahead with any question you have. Can the world survive without fossil fuels? What are the alternatives? Question from Giovanna. I think the simple answer is yes, it's not a problem at all. Because what are the alternatives? Let's say it this way. We will have to survive without fossil fuels. Because fossil fuels are by definition almost exhaustible. What are the alternatives? Simply, renewable energy. If you look at the basic physics, then the amount of energy that we receive, that the Earth as one system receives from the Sun, the amount of energy is very much larger than what we use. It's a factor 100 or 1,000, I don't know precisely, but it's really very much more. So the only thing that we need to do is to kind of capture 1% of the energy that the Sun sends to the Earth. If we would be able to do that, we would have more energy than we could ever want. So if you look, and the question is that feasible or not? And my view is that that's feasible, that's not problematic at all. If you look at our history, I didn't show a picture, but if you realize that currently we in Europe, we are about 10 times as rich as that we were 100 years ago. And we are about 50 times as rich as that we, then, no, not 50, 40 times as rich as that what we were 200 years ago. Now, where does this come from? Why are we now so rich compared to 200 years ago? That's because we invented all things. So, the Industrial Revolution, many people think that the main element of the Industrial Revolution is that we mastered energy for production. But you could also say the main part of the Industrial Revolution is that we set up an economic system where we started to use knowledge on purpose, or knowledge creation on purpose. So what did we discover? We discovered that if you have an entrepreneur and you allow the entrepreneur to reap the benefits of devising something new that works better than something that was there before, then that entrepreneur will look for something better, and he will make better machines and he will make better products. So similarly, the very moment that we decide that we should stop using fossil fuel energy, I'm sure within 20 years we'll have very, very well functioning, cheap alternative energy sources. I have no doubt at all. I'm very optimistic on that. And it's very hard to say what they will be precisely, but tell me, who could have told 50 years before that we would have computers? Who could have told 20 years ago that we would have mobile phones with apps running on them? No one. It makes no sense in a certain way to try to predict the future too precisely. The only thing we can predict is that we have a market, an economic market that functions well in one respect. That if there is an opportunity to develop something new and you can earn money from it, then firms will do it. So I hope that that answer is more or less the question. Giovanna, if it does not, you're welcome to extend the question, and everyone else is also welcome to come up with other questions. Thank you, Brian. Are there other questions from somewhere in your rooms? Thank you, Giovanna. Please, students, you have the opportunity. Come on. Ask anything you've ever wanted to ask before. Okay, Giovanna. What do I think about the future of greenhouse effect? Do you mean what I expect that will happen? And you can simply answer yes or no. Is that the question? What do I expect that will happen with the greenhouse effect? Okay. Thank you very much. So my personal opinions. So my personal opinion is that, well, I think I have no reason to doubt my colleagues from natural sciences. So, and what these people from natural sciences say, they say that because of the direct effect of CO2 is very clear. It's about 1 degree Celsius for a doubling. And then they say that the only way that you can explain the huge temperature differences between the ice ages, that's 10 degrees Celsius, the only way you can explain that is because of strong positive feedbacks. So my personal opinion is that probably there will be substantial positive feedbacks, and probably the temperature will stabilize for a few more years because you could see that in the cycle, but then say by 2020 it will take off again, and most probably temperatures will skyrocket until the year 2050. And I actually fear that that by the year 2050, I would expect that at some point the people would say, yes, well, we have been quite stupid in the past. This is really not handy what we've been doing. And at that point in time, they cannot anymore, because there's already such an amount of CO2 in the atmosphere. There's not much we can do about that. So what they will do is they will do what we call solar radiation management. And the basic idea of solar radiation management is that you try to prevent solar light from actually entering the atmosphere. So we'll most probably blow up aerosols high into the atmosphere, which will act as a kind of a mirror outside at the outer skirts of the atmosphere to mirror back 1% of the solar sunshine. That will be quite risky, but at that point in time, we'll think that will be less risky than letting climate change run its progress. So, as a scientist, I say you live really in the best of times because we are running an enormous experiment, an experiment that will probably run only one time in the entire lifetime of the Earth, and that's the experiment human-brought climate change. You'll find out because in 70 years' time, we could expect climate change, the enhanced climate change effect to be on its strongest if we would start reducing emissions, say, in 30 years' time. So you will see more of it than I will. And well, whether we will be able to take joint action as a world, well, I'm a bit pessimistic about that. I think that sadly you've seen the same in Italy as in the Netherlands. You know, when it comes to policy making, then it seems that populists find it the easiest to get their voice heard. And populists in the Netherlands, at least, have a very simple argument. In the Netherlands, they sometimes explicitly say, you know, if you don't understand it, then it doesn't exist. So they don't understand climate change, so they simply say it doesn't exist. So I think that's the same in many countries. So in that sense, I'm pessimistic. So the next question, Brindisi, what's the best renewable source in my opinion? I don't think it's useful to think of the best renewable source. I think we should use all renewable resources that we can lay our hands on. So, and it also very much depends on the location. Typically, I would expect that in countries with lots of sunshine, and so that might apply to Italy, but it will surely apply to many countries around the equator. Direct solar energy is probably the best renewable resource. So directly converting sunlight into some storable form of energy. It could be electricity in kind of a battery, but it could also be a kind of synthetic fuel. I think that will be in 100 years' time, I would expect that to be the case. Thank you, Giovanna. So so to continue that, so I think that in 100 years' time, you know, fossil fuels are finite. It's as simple as that. So I always say, the only question is not whether we have to transform from fossil fuels to renewables. The only question is when we do it. And and obviously many people want to delay it as long as possible because they can make huge profits. But on the other hand, well, if you know that you have to do something, in many cases you may say you can better do it as quickly as you can. Yes, so I strongly think that indeed renewable energy, the question from Federica, I think that there is no basic natural scientist physics reason why renewable energy should not be able to supply energy in the future. I don't see any fundamental problem. You know, the main problem that is that researchers discuss is the storability. So the problem of solar and wind, etc., is that they produce electricity. But electricity we can only store in batteries at this moment, and batteries have they are very costly and very heavy, etc. So what I would expect is that in the future that we develop a kind of synthetic fuel. So my expectation is that there will be synthetic fuel. So you should think simply of petrol, but not petrol made from oil and not petrol made from crops, but petrol made purely synthetically, kind of made from the CO2 from the air. So that's what I would expect in the future. And once we get that system working, I don't see any problem. Well, the reason that the USA, so that's a question from Nicola, that the USA did not sign the Kyoto Protocol is simply that the majority of the people in the US, they don't believe in climate change. And well, one of the reasons possibly is but this is now I'm talking personally, so I have to say up front, this is my personal opinion. This is not output from my research. But I have the impression that if you compare Europe, for example, to the US, then many features of the US are, from the European perspective, like a developing country. So you have the huge inequality, and you have a huge number of people who actually have a very low level of general education and who have a very national, domestic view of the world. So the typical perspective of a US citizen is that he or she only looks at your own local concerns and possibly the national US concerns. But what happens outside the US, that's really, they don't find it of any interest. So in their perspective, Kyoto is simply a mechanism by the foreign countries to scare the US. That's how they view climate change. So they don't view climate change as a real natural phenomenon. No, they think that climate change is some kind of conspiracy that the Europeans set up to rob them from their wealth. Well, there's not much you can do about that. But as long as the US people, as long as that's their main idea, no president in the US can ever sign the Kyoto Protocol. They are bound by what the citizens believe. So this is a bit a cynical perspective, Nicola. So that's why I emphasize that this is my personal view and not so much my research output. Okay. Well, if there's one quick last question, then I'll happy to answer it, and otherwise I'll have another meeting coming up in 5 minutes. Is that okay, Andrea? Yeah, well, thank you very much. It was a bit of a pity that you couldn't connect to your videos. I would have loved to actually have an idea of who I've been talking to. It remains a bit odd to talk just to a screen without seeing anyone. I work a lot with Skype, but typically I know the people. But thank you all very much. I hope you enjoyed it, and well, you never know. Maybe you'll study at some theme institute and you'll meet me in the future. Thank you. Okay, Nadia. Well, who knows? Bye.